Alright, time for another DraftPhysics.com video presentation. So, I think I'll play a Julius Sumner video eventually. Uh, this bar's got a new scale, so we can talk about scales and momentum. But I think I'll just re-emphasize what I think the conversation needs is this simpler proof of their theory of this extra energy. Now, that simple proof could come with them just proving it takes 4 times the fuel to move something twice as fast. Somewhere in the annals of physics, somewhere where they could demonstrate that that's actually true. But all of this also, I think, is a pretty decisive demonstration. So this example of the, I guess this belongs down here, and this goes over here. I mean, this example of the gun and the bullet, I mean, it's in your face as an example, because it's clear that they concede that this momentum stuff, this action that happens equally on both sides. That there's this Newton's third law: for every action there's an equal and opposite reaction. And that, and I've explained that that's really made out of 2 things. The fact that everything that explodes, anything that just expands in the universe, would expand theoretically in all directions, and therefore you have an equal and opposite. And then the other case is that I hit you, we share our condition, and by being in contact with each other, and that I either lose or gain, okay, in that exchange. And if I gain, the other thing lost. If I lose, the other thing gained. And that's the equal and opposite reaction. Is if I put money in a soda machine, the soda machine is richer and I'm automatically poorer. There's no opposite reaction that takes it away from me. I lost it by giving it away. That's simple. So the gun and the bullet don't make any sense. So just the standard gun. Now in this example, I'm just exaggerating the 2 circumstances. What if I shoot 2 bullets with the same explosion, or I shoot 2 guns? Their theory says I only have 4 joules from the explosion in this case, and I have 4,000 joules in this case. I mean, obviously, that on its face doesn't make any sense. The explosion had so many little particulates flying out at so much velocity, flew out in both directions, pushing both objects because they're equal mass. And, I mean, you can't contrive any differential in the sense that they're both going to be affected based on their mass, and that they're both going to absorb the same amount of energy. But how can I have this gigantic 1,000 times difference in how much energy the explosion produces? And so they won't draw that and explain how that's possible. How it's possible that because I just put lighter things in front of the explosion, that somehow I derived more energy from the explosion. It doesn't make any sense. I don't see any theoretical ground to argue it. How can you defend it? This 4,000 number's made up. They don't have an experiment where they collect the 4,000, let's call them watts, where they collect the wattage of the bullet and they collect the wattage of the recoiling gun. There's no experiment. And let's understand, every time a gun goes off, and somebody's holding the gun, it's a recoil that you can see a little bit of because their whole body is absorbing the energy. So the gun goes from being a couple of pounds to being, 100 or 200 plus pounds. Because you're moving lots of pieces of the human also. So if you just let the gun fly, it'd be a better illustration. If you could see the gun just fly off like you see the bullet fly off, you get a better appreciation for how much energy is actually in the gun and how much energy is actually in the bullet. That the difference isn't as extreme as you think in terms of the gun will look pretty energetic. But yeah, it just doesn't, on its face, doesn't make any sense. And then I, give the spaceship example. Okay, you have a spaceship and you shoot out one side, the 5-ton train, so to speak, the 5 mass going 10 velocity, the inverse relationship. All you're looking to do, it doesn't matter what the weights are, you're just inverting weight and velocity. They say this has 2x the amount of energy. The lighter object has more energy. Yet then I think most of them, I think Puro would agree that the spaceship isn't going to be moved. If I do this experiment in space where from one side of the ship I shoot out the 10 mass going 5, and from the other side of the ship I shoot out the 5 mass going 10, the kinetic energy, the equal and opposite reaction, isn't going to show up. Newton's third law is going to be abolished through kinetic energy theory. There is no Newton's third law. And I'm not going to get any 2x the recoil. It's not going to happen. It's not going to exist. The equal and opposite reaction will not exist because the ship isn't going to turn, because it's space knows it. You people don't know it, but empty space knows that this is the same as this. Okay, it figured it out. Nature knows that this is the same amount of movement in the universe. It's the same amount of force ultimately in the universe. The two objects have collected the same amount. They've just spread that amount on a different amount of mass, meaning that the thing goes a little bit slower because it's spread a little thinner over a larger mass. But it's the same amount of butter. All you can do, you can change the amount of bread, but you can't change the butter, the force that they're constituted with, that they're covered with, that makes them move. It's the same. And one of them doesn't have, one of them's not going to light more light bulbs, one of them's not going to do more work if they're in a tug of war. So that experiment was also done. I mean, Toady did it. It wasn't the greatest, but it was good enough, filmed on an iPhone, where he did the Newton's cradle. And basically said, here, I'm going to put one side, I'm going to give more energy to one side than the other. And the theory would be is that the one with more energy is going to move, the experiment. The lighter thing with more energy should be able to push right through the bigger thing with less energy, less momentum. And it doesn't happen. Okay, it doesn't win the tug of war. You collide the 10-ton train going 5 miles an hour into the 5-ton train going 10 miles an hour, and the 5-ton train doesn't show that it has more energy. It doesn't push the collision in its direction. It doesn't win, plain and simple. So again, another example of it doesn't work. There's no proof. There's no evidence. Again, they haven't done any of these experiments. To just argue right there isn't kind of amazing that they've done none of these experiments. So we have all these different devices that can convert. So now we get to the lever argument. All these devices that can convert one momentum into another momentum, a gear or hydraulics, all these mechanisms, and I haven't used any of them, okay, to show us the reality of this kinetic energy theory. And so the simple argument is that yes, if you swing the 5 mass going 10 into the lever and have a 10 mass that would go 5, okay, based on the position of it, 1 unit of distance, this is 2 units of distance, it'll do the conversion. This acceleration will be twice the rate that this is, which is exactly what it needs to achieve the faster velocity. The Newton's cradle can't do that, can't do the conversion. This is doing it for you. Newton's cradle is requiring the bigger object to accept energy that it can't accept. It's a velocity it can't go. So the energy has to bounce around inside of the object to get to the right velocity, and in that process ends up reflecting because it just can't absorb the velocity. The acceleration rate is faster than it can accelerate, so it can't accept the energy readily. It can only accept part of it. But the lever fixes all that. And there's no explanation for how it's possible that I can destroy the momentum. That is, I can put the 10 mass in and somehow not get the 5 mass going twice the velocity out. Well, where did it go? The fulcrum isn't going to see it because the fulcrum is saying this weighs the same as this. It's balances just fine. So it sees it as the same pushing force, the same obstacle, And so there's no explanation. You can do this with springs, lots of things. So I guess we'll get to springs. So I just thought, since I had these, I mean, these are simple things. They could argue. They could argue the lever. They could argue the gun. They could argue the spaceship. And they could explain where I'm saying something that's inaccurate, that I'm wrong. We'll explain where I'm wrong. Point out where I'm making a point that isn't a valid point. I think it's a very valid point. You say the explosion creates 2 joules in one circumstance and 2,000 in the other. You should be able to explain where all that energy went. All right, I mean, it can be cut down to just one atom, right? I take this zip gun and I put one atom more on one bullet, just one more atom, and all of a sudden I've made the other bullet more powerful. Just one more atom, because anything I add that's going to slow down the velocity any amount because of the square term in their formula means the other thing has more energy. It's losing energy because I added mass. You don't lose energy because you add mass. And when they combine the two objects, that experiment sort of just proves it. I mean, it shouldn't even be an argument. I mean, I can combine a 5 and a 5, and they'll concede what happens. I mean, a 5 and a 5, and I'll end up with a 10 going half the velocity, which makes perfectly good sense. 10 velocity, 10 velocity. I mean, 0. So I take the 5 coming in, going 10 velocity, and I get a 10 going 5 coming out. So they're conceding the conservation of the momentum, and they're saying that somehow half the energy was lost. Well, there's no explanation for how half the energy disappeared. There won't be any demonstration of how this has half the energy, that it doesn't do just as much work, that it isn't just as a significant amount of force that you could peel off of the matter. Yes, you're peeling less force off more matter. Here there's less matter and more force per piece of matter. But you're peeling off the same amount. You're taking back the same amount. To take away its force, to take away its energy, okay, they are the same thing. I don't know how anybody can argue they're not the same thing, that force isn't exactly what energy is, and that isn't exactly what momentum is. All right, so that sort of gets to the dispar and the scale thing, and just this couple of points I'll raise. Experiments that I think would be useful to do. Yeah, so I will erase, and we'll get to that. All right, I'm back. So this is a clip from his video. So he got a new scale. And I'll play this a little bit.
It's way bigger than this scale. Yeah, I am crazy. The things that I do to discover truth.
Discover truth. Yeah, I don't think that's what you're trying to do, but whatever. So yeah, there's lots of things to consider though. Yeah, it looks bigger, it's nicer, you can do heavier weights, all that kind of stuff. You can even unscrew the plate with just wing nuts and put on a different plate, which would be a good idea, frankly. But you don't know what, the problem with these scales is they're made to weigh things. They're not made to weigh impact weights. And so they usually have some kind of dampening device to stop it from oscillating, and that's the downside of attempting to measure impact weights, is the dampening is going to have some effect. And so this is all stuff that needs to be researched. And frankly, the configuration of this scale isn't ideal for putting it horizontally, which I think you really need to do a few experiments where you just are measuring the weight of momentum. Frankly, because that's a big part of this whole conversation, is we're really trying to figure out if momentum is weight. And if it is, that's a big tell, because then Hooke's law pretty much dictates that weight is force. But anyway, fine. Have at
find
it.
out the truth. A really professional one. It can be pushed all the way to 10 kilograms. It also is in pounds.
So again, the real thing would be it'd be interesting to be able to drop a weight on a scale or a spring and see how much of the energy you actually get back. I mean, how much do springs actually conserve? So would the object fly back up at the same speed that you put it in? How close can you get to that scenario? Because that's a real good measuring spring. All right, so all of this is there's all kinds of things to all kinds of unknown variables built into this scale in terms of how it's constructed. It probably has some little lever in it that's actually doing the pressing on the spring. It's either a coiled spring or it's a looped spring or some other kind of device. So all of that's part of what you have to appreciate in terms of what you can actually measure with the scale. And I don't know if you've really thought about any of that crap. Frankly, some scales actually have a suspension, because once the weight's on it, you're just measuring the relative difference in one part of the scale. So you have to make sure it does ground well in terms of not having shock absorbers of some kind, because the whole point is you want to measure the shock. So you don't want something else absorbing the shock and such. It clearly has some dampening. I mean, it doesn't oscillate very long, and that's a downside. You'd really want something that allows the weight to oscillate on the scale, and that makes the whole thing, like I said, the dampening is probably going to, in some respects, affect the results. How much, I don't know. I don't know. Anyway, we'll see. Whatever. I just figured you have to do this more. You have to get more to the crude mechanics. You're just using a spring to measure momentum, and that's all. And so the more pieces of hardware you have attached, the worse. So probably if I was going to buy a scale, I would get one of the measure the weight of a fish kind of scales, because they don't have all of this extra hardware. But anyway, you didn't ask my advice, so I won't provide it now because it's too late. Anyway, all right, so so I'll just talk a little bit about the difference. I mean, I'm arguing basically that you could duplicate what gravity does, okay, in terms of a weight, by just putting a momentum into a scale. So if I can take 100 pounds and I can move it 9.8 meters per second, technically, okay, what I should end up with is 100 pounds on the scale. Because technically that's why we weigh our mass, weight. It's why it equals, because at this velocity, okay, 100 pounds in mass will have the energy, okay, the momentum to get a spring to compress where the needle says 100 pounds. All right, so the correlation is connected. So I can duplicate what gravity's doing for a millisecond. I can get it to go to the 100 pound. It won't stay there. It'll bounce back. And again, that's the interesting part. How efficient are springs in terms of accepting a weight and then rejecting a weight? So again, this is something I would do with a pendulum, because frankly, they're pretty lossless in a lot of respects, and swing something into the mass and therefore evade frictions and rolling and all the other things that are a liability to getting an accurate reading, and just see what happens, right? See how many bounces you get out of the weight, and that again is going to depend on how good the spring is, I guess. It's not an outrageous guess, I would say. Yes. Oh, that's a little bit shy. And it has a reflection in it, which isn't great either. All right, but anyway, so those are the kind of comparison experiments. So obviously, if I swung this down to here, okay, and I did the same thing, I'm going to get an impact weight, but then it's going to also, because it's a sustained constant pressure, that's what it's going to come in plus, okay, it's going to have the plus value of the constant force that's also gravity. So you're not weighing just the momentum, you'll be weighing the momentum plus gravity. So that's why I think the two numbers will be different, in the sense that this falling will push the scale to a level, and then the scale will go back up to it's the weight. So this would be 100 pounds, and any distance is going to be an increase in the weight. So any amount of time it falls. So if it falls, so I let it fall the full meter to get the 9.8, right? Is it a meter? It has to fall. I have to think about that. It has to fall for a full second. It falls 5 meters a second in a second. So it has to fall 5 meters to get 9.8 of velocity. So yeah, I'm going to get the 100 pound, I'm going to get a much larger 200 pound reading by going whatever, 4.8 meters. Alright, so this is where it gets complicated, right? Because to double the weight, all I have to go is 1 centimeter, actually. Right? That doubles the weight. So 1 centimeter will double the weight. And 1 centimeter is a lot less than 9.8 meters per second. So that doesn't make any sense. This is wrong, because that's 9.8 meters a second. And the velocity I have to create to duplicate, yeah, that duplicates 5 meters. Okay, yeah, so that's right, 9.8. So that's 5 meters at 9.8 meters per second. The velocity when it hits, yeah, I don't know what that velocity is. Got to calculate that. Yeah, so I don't know it. I don't know what the velocity is after dropping 5 meters. But whatever that velocity is, that's the velocity this needs to go, okay, to weigh 100 pounds. So 100 pounds needs to go that velocity to weigh 100 pounds horizontally, okay. Well, anyway, so those are the experiments I think need to be done, but regardless, what else is there to say about it? I mean, it just proves, you know, weight is momentum. All you're measuring, when you measure weight, you're measuring something's momentum. And as Newton understood, momentum is force. Okay, you want to double something's velocity, you double the force. I mean, Newton was made pretty clear in his second law explanation that a force is just equals the mass times the velocity. In the sense that if you want to double the velocity, you just double the force. And the mass is the constant in the experiment, you're not changing that. So clearly, that's a huge correlation between the two. Undeniable. And I would argue that that also just equals the energy. The energy is the force. You can't have half the force make twice the energy or any kind of nonsense like that. Alright, that's probably enough of that. And so we'll move on to the Julius Sumner video. Alright, I'm back. So, his first episode was on center of gravity, and it's really not that, it's not that interesting. I mean, it's interesting, but it doesn't have much to do with this energy stuff. So, we can skip that. And this is Newton's first law. And I've no doubt done this before, but whatever, we're going to do it again. Start now.
How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today
is propaganda. Yeah, it's just whatever. So I would argue that all of this can be understood and interpreted with different words, and I think stated better. So Newton's first law is that something in motion stays in motion. Now the idea of the something is the tricky part. You want to say elemental motion, something that has elemental motion. Because I can make an engine and I can make it run and then it'll run out of fuel. So I could even have like a little decaying isotopes, and I could build a little device, that the rays almost, they hit this piece, but they don't hit this side, and so then the object is getting hit in one direction. It's not getting hit in the other direction, so it'll move in a direction, and eventually the isotopes run out of decay energy, falling apartness, and the thing stops. But the rest of it is this is just the exchange argument, and so you need another force to interact with something, and it's just how well does it interact, how much of an exchange does it make. Does it have really good contact? Does it have angular contact? What kind of contact it has? And that's going to dictate what kind of exchange is going to be made between the two objects. But it's going to be clear, in my opinion, that again, it's just a matter of money. You could think about it as currency, and you could just say it doesn't matter which one has the currency that's causing the crash. Whether this one's moving into this or whether this one's moving into that doesn't really matter. What's going to happen is somebody has the real money, and what's going to happen is there's going to be an exchange in the money. And that's all. I don't need to make this one poorer with some extra other force. There's no counter force that causes this one to be poor. The force, as it gave its energy to something else. The force is a substance, and the substance just moves two different things into different pockets, so to speak. It's just money, and there's banks, and period. And everything has a bank size. You could just argue that some banks only hold nickels, some banks will hold dimes, some banks, So the amount of energy the amount of how you convey your currency depends on how much mass you have and how much acceleration you can smoothly accept. And so if you have to do a bunch of currency exchanges, you have to change a bunch of nickels into dimes, or vice versa, you're in trouble. You're not going to have time to do the exchanging.
A is the subject of inertia, and I must
Yeah, so again, then the word inertia is meaningless. Frankly, it doesn't say anything. There's no such thing as an inertial force or an inertial anything. All there is either something is moving or it's not moving. And the fact is it's a mass that moves. Okay, so mass is half the equation. The movement's half the number. The mass is the other half of the equation. And you're just saying what's the combination. And the combination will tell you what the total force is.
Make the matter, the idea clear as follows. Here we have a block of wood at rest on the tabletop.
So he has a briefcase behind him, so maybe one of the examples he was going to give would be holding it and saying, I'm not doing any work. That would be silly.
And I ask, what does that block want to do? Answer, the block wishes to remain at rest.
So it doesn't wish to do anything. It's just a matter that it's a lot of atoms. And to make the atoms move, you have to give them all a little bit of energy to do it. They all have to agree to move, essentially. All the atoms are connected to each other by a very quick speed of light force. And basically something comes in that says we're going to move. If they're all agreeable, if each exchange means that everything moves just fine, and the energy just goes through at the same speed, and gets to the other side, then the whole object will move. But if the transition, that is the speed, doesn't fit and doesn't move through the object, then the whole object doesn't agree to move because it has too many pieces of matter that have to change the velocity. The velocity is too high, so some of the little pieces are moving very fast, but all the rest aren't, and therefore the object isn't going to go anywhere. So it's really just about how efficiently you can apply the force to another object, and it's always inefficient when you have to change how many atoms are being affected.
Supposing now I have double as much block, and I try in turn to put that system in motion. What do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much, and therefore we say
so this idea that it's all just 2-to-1 kind of things, it's not 4-to-1, it's not 4 times, it's not, it's 2 times, twice. Two things twice as much, not 4 times as much.
Its inertia is twice as great. And so you discover at once that I have used the term inertia.
So there's no inertia, and in space you could just tap this thing and it'll go wherever, it'll absorb the amount of force you apply. It will be applied to all of its little elements, and it will in fact move. So it's not going to be a problem. And it's only when you get extreme differences between the impact force and the object that you get reflections. So things will start bouncing off of stuff when the stuff gets heavy enough, where it won't yield at all. And that's just basically because the surface finds the velocity way too high to even communicate between the atoms. The atoms start breaking. If you start breaking the atoms, then you really know you're not going to be able to get the energy through the object. So you end up reflecting the energy.
And referred to the idea of mass as synonymous. So
that's for Ian, okay? This is Professor Julius Sumner saying to you, okay, it's just synonymous. Mass is inertia, so you can't play this game that a 5 mass has more inertia than a 10 mass. No, it doesn't. I mean, it has more mass. It has less mass. Can't have more inertia, right? How can a lighter thing have more inertia? Doesn't make any sense.
Mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do.
And yeah, so we all use this kind of language about a want, but the fact is that it contains a force, and unless there's some way you take the force away, it's stuck moving. The atoms have been changed. They now have this force on them, this differential in them, and now this is what they're going to do because that's their configuration until something opposing that hits them or something adding to that hits them. But they have to have contact with some other object that also contains force, and that object conveys the force, or else the force itself, like gravity, affects them and just directly adds force to them. But the force is real stuff in the universe. I mean, I know that you cannot believe that for some dopey reason, but yes, the force is real, okay? It's real stuff, and the fact is, it sticks to matter.
In English, simply, whatever a body is doing, that's what it wants to do. Let's look at Newton's Latin for it. Newton put it in Latin. Axiomata.
Not very useful.
Siva legis motus. Axioms, even laws of motion. Corpus omne perseverare in statu suo quiescendi, and so on. And in English, a little more within our competence. Every body continues in its state of rest or of uniform motion in a straight line, unless there are some forces to divert it.
Yeah, and the forces, okay, are in the form of either a force like gravity or photons or something moving the speed of light, some elemental tiny discrete bits of force, a field of those, or it hits another material body that has a force condition, and it will the attempt will be made, the opportunity for an exchange takes place, and depending on how compatible the two differences in the force they contain is, they can be exchanged. So if they have the same mass, they can do lots of exchanging because the velocities will be, the acceleration of one object will equal the deceleration of the other object. The way it gives away will be the same speed it's giving. And when those speeds are different, then there's going to be only a partial exchange.
Consider now the following. Here you come on April Fool's Day, let us say, on two packages resting on the ground.
So, I know we did this a couple months ago, but whatever. Yeah, one with bricks and one with whatever, old shirts.
Here is one and here is another. And you deliver, you impose a force on the one. I will, instead of with my foot, with my hand, and it experienced such a motion. The force produced a motion in the body of so much inertia. Now I try it with this one. Hardly as much.
Right. So obviously it's more mass, more little atoms to move, and you're putting a speed in that if I tried to move all the atoms at that speed, I'd have to have more energy, more force. I don't have enough force to spread it. So it can't move at that velocity, and so it has to incrementally say, yes, I can move 1 mile an hour, so I'll go that. I can do that. I can do 2 miles. I can do 3 miles. And then there's a point where it can't go to that 4th or 5th mile because it requires more energy. And all of that takes time. And so the problem is it can't absorb all of the force because it doesn't have enough time being in contact with the object imposing the force.
Motion. Why? This one is filled with rags and this one with 2 bricks. And this one has the greater inertia. So, the measure of the mass.
Everything else is just about reflection. So the lighter you make it, the easier it is to get the force in because there's a tiny bit of matter to move, okay, and it's fairly easy to make it move the same speed you're moving. You only have to give up a tiny percentage of the energy you have. But the heavier you make it, now the harder it is to get that velocity into the object, and therefore you end up hurting your hand because of the reflection. Now it's going to start reflecting your energy back at you because it can't absorb it.
Mass of a body is its inertia. Consider now the 2 aspects of Newton's first law. A body at rest wishes to remain so. Here I have a heavy block of wood, a hole in it, and I put a dowel rod in the hole. The dowel rod constitutes the handle. How can I put that handle into the block? As follows. As follows. Notice what happens. I hit the handle. The block remains at rest, whereupon the handle moves.
So it's just 2 different exchanges, and one of them you're using a heavy thing to smash into a light thing, only partial energy again, and then the big block is bigger. It's not going to move at the same velocity. The stick is going to move in. The stick is going to end up going faster than the block, and all you have is friction to make the transfer through. And it's, so you're going to end up moving the stick faster than the block, and it will go through it because you gave the stick more energy than the block can absorb.
Into the block. That's the first law. The body of large inertia wishes to remain at rest.
So it's just saying no. It's just wrong to say. It doesn't wish to do anything, but do exactly what it's doing. And you're saying, okay, the only way I can make it do something is I have to give it energy. I can't not give it energy and make it do something. I have to give it the energy. And that's it. There's no law saying it won't. It doesn't want it. It's just the fact that you have to give it in a denomination it can use. You can't give it a $10,000 bill and say, go to the store and buy something. You can't do it.
Let me pursue this in another way to demonstrate the second part of Newton's law. What did the second part say? If the body is in uniform motion in a straight line, that's what it wants to do. I start again. Now I come down on a firm block. The motion of the handle is arrested. The handle and the block were moving. And what does the block want to do? Keep moving. Whereupon it lost.
So it obviously has energy in it when you're moving it. So you put the energy into it, and now it's having it's having a problem getting the energy into the other object because it's so massive, because it's tied to the surface. So it can't get the energy in, and it just keeps its energy, and because it can't get rid of it. It's a bad Newton's cradle again. So you can just see all of this with a Newton's cradle, that you can't transfer energy efficiently between uneven masses.
lodges itself more firmly on the handle.
Unless you use a lever or gears or some other mechanism to convert the difference in their deceleration versus acceleration.
Thus do we demonstrate Newton's first law in...
I suppose that's worth just be interrupting and saying, okay, I'll just draw that one more time and say it one more time, because to me it's a glaring, okay, piece of the logic into understanding why levers work or why gears work, is for the simple reason, okay, that you can understand that that's what they're doing. They're doing the velocity conversion. That's all they're doing. You're just saying this has a velocity, the 10 mass, all right, going 5 velocity, coming down, and you're just saying that has a momentum, but it's based on this 5 velocity, and then you can say over here you want to put all of the energy into the 5 mass. Well, to get all the energy into the 5 mass, I have to convert it into a higher velocity. So this one's acceleration is going to be twice. It's going to move twice the distance in the same time. This moves this distance. This will move twice the distance. So the acceleration of the 5 is consistent with the necessary, okay, 10 velocity, okay, that this one's going to need to convert the energy. So as this one decelerates based on its 5 velocity, this one will accelerate, okay, based on the 10 velocity. So this accelerates at twice the rate, and this one decelerates at half the rate, half the speed of deceleration. So this one's, you've matched the acceleration to the deceleration, just as if you hit 2 equal masses in a Newton's cradle, and you get a full exchange. All the energy goes from one object into the other object. It's a complete exchange because the two accelerations and decelerations at contact are exactly the same. So you got an easy way to transfer. The mass to mass ratios are the same. So for every little bit of mass here, you have a parallel bit of mass here, and each will just accept the velocity that these atoms had. These will accept that velocity as a group. Their capacity to move collectively is the same, and the lever fixes for that in the sense that it just adds this, the rate of deceleration here will be the same as the acceleration here, and not the same. It will be proportional to the mass. Half the mass, twice the velocity. Pretty much simple enough.
2 parts. Let me do this another way. Very pretty. Very pretty. I have a support and a weight W supported by a string and another string with a loop in it here, which I shall show you. Let me call this string A and this string B.
Right, so Professor Lewin did this experiment. This is, kind of another show experiment. And I don't think they exactly explained the simple point. I mean, the point is the speed is basically forcing a conversion that's, it can't do. And so it's just basically showing without enough time, okay, energy doesn't have time to move from one place to another place. It can't see something it can't know exists, a circumstance. So if there's no time for the energy to get to another place, then I don't know how to put that. Then yeah, the string has to break because you're putting the energy faster than it can transmit the energy, I guess is the simple point.
I propose to do as follows. I'm going to pull on string B, the lower string. And I can break either string B or string A by invoking Newton's first law. If I pull suddenly on string B, W wishes to remain at rest and B will break. On the other hand, if I pull gently on B, A supports, W already there, plus the force I impose. And I shall show you that.
So I don't think this really shows Newton's first law. That's what I was just saying. This just shows that it takes time, okay, to transmit the information, okay, of a impact. And it's just basically showing you that if the impact doesn't have time to migrate the pressure to some other location, then the thing breaks. So this is more about tension and, you know, surface of something's crackability, so to speak, is the fact that it can't spread the energy quickly enough. It's like too much electricity melts the metal. It's like it just can't handle it.
Exactly with this demonstration. Here is a string, here is a hook, here is a weight, and the upper string is supporting the load. Here is the lower string, and I am putting a little rod inside here so that my hand is not underneath should the weight fall. I am going to break the lower string. Watch it now, the lower one. There it is, I broke it. Now,
and so all that really happened is that the big weight had no time to negotiate the pressure to the other string, because it has to go through so many different atoms to convey how much pressure there actually is. So it never got there. And so the string is basically stuck with all the energy and a reflection, and it can't take the amount of pressure. But if you give the pressure time, okay, you go through this object and then get into the other string, then you can break the other string, okay.
I am going to change the string. I'm going to change the string. And now I am going to break the upper string by pulling slowly on the lower one. Watch it now. Watch. We hope that breaks. Now, supposing it does not. One is led to say the experiment has failed. And I say, no, the experiment doesn't fail. I have failed to meet the requirements of nature.
Well, that's the same thing, frankly. I have failed and the experiment has failed. It's same difference.
Watch, I'm going to break the upper string. There it is. And so we can be applauded for success. Consider another demonstration of the
It's going to keep doing the same thing, but okay.
same. Here is an enormous weight, 16 pounds. Here is a string attached to it. If I pull on that string in a gentle way, I'll do it by hand, in a gentle way, the string can support the load. Now let me try to accelerate it. What does Newton's first law say? Body wants to remain at rest.
So there's two different amounts of energy being put into the string. So, you know, obviously in one case it wasn't enough energy to break the string. In the second case it is enough energy to break the string. Not that complicated.
It has enormous inertia. Watch it. Do you see? The string has broken. I shall have more to say about this when I talk about Newton's second law. The second law. Consider now another dramatic...
So when he talks about the second law, unfortunately, he just talks about momentum more than anything else. So it's, as much as he says it's F equals ma, he doesn't go into the squared crapola.
Demonstration. An application of Newton's first law, because we must not escape the fact that these laws of physics, of nature, of science, have vast applications in...
Except you haven't done any of these basic experiments demonstrating that some of these laws or these formula are real.
Being things. A brick, a trowel. Cannot the craftsman, the bricklayer, utilize Newton's first law in this way? Notice if he hit his hand with the trowel, he'd hurt it. But he can hit the brick with absolute abandon.
Why would he do that? Sorry, I don't understand. What does that have to do with anything?
And feel nothing. Inertia of the brick. Here.
All right, so he's saying that the impact force, that somehow it was the momentum that would have hurt his hand. Obviously, it was not the momentum that would have hurt his hand. It's the fact that it's a very thin piece of metal, and it's applying a very a large force over a very small contact point, and the small contact point will mean you'll just rupture the atoms on the surface. So it's not the momentum that's the problem, that he was hitting the brick. So this isn't really a first law thing again. It wasn't that he stopped the momentum from hurting his hand. He stopped a sharp object from hurting his hand. So it was kind of a lame demonstration. I mean, obviously you could put a brick in your hand and then somebody could throw a 90-mile-an-hour baseball and you're not going to feel much. But that's just because you've created a ton of stuff that has to be moved by the baseball. So you've just allowed something else to absorb the energy.
Here's another classic, which I like to do because it is so dramatic.
This one is good. So this is really good.
Sheet of paper, about 20 inches by 30. 20 inches by 30. 600 square inches. The load on each square inch is roughly 15 pounds. Atmospheric pressure at sea level. Therefore, about 9,000 pounds of air on that paper. That's it.
It's a kind of bizarre thing to think about. I mean, obviously there's the same shooting up from the bottom as there is coming down from the top of air pressure. But, when you think about it, if you had, literally, the fact is if you try to move this piece of paper very quickly, there's no way it's going to happen because it's a lot of air you have to move.
Enormous inertia. Proof. Here is a board, 1/4 inch thick. I put the board under here, and now I am going to try to put that enormous mass of air into motion by a sudden impulsive blow on this end of the stick. The impulsive view that people have is, oh, the whole thing will catapult. No, it will not, because that mass of air is at rest, and Newton said it wishes to remain so. Watch it.
So the more, more interesting thing is the paper doesn't tear. So the paper is able to spread the energy, without just tearing where the board is. So that's the other part of it that's interesting.
It did not move. It did not move. Fantastic. Now, remember, ladies and gentlemen and boys and girls, when I refer to this...
They really should have gotten him in a, air-conditioned studio, but whatever. He does sweat and drink a lot.
Being at rest. And then I say, what does it want to do? And the answer is it wants to remain at rest. I would not have you dispose of this as trivia, because it took the genius of an Isaac Newton to establish it. Nothing trivial about it.
Yeah, it is sort of important to understand why it moves, and the fact is you have to give it force for it to move. If you can't give the force, then it won't go anywhere, but it's just a matter of getting the force into the object. There's no, I don't want the force. So the more compatible the force is to the condition of the substance in terms of its ability to absorb the energy will decide how much it wants to move. And if you apply the force in too aggressively, like a bullet, the wood just flies into little pieces. So yeah, if you're too aggressive, you're not going to get the force in. But if you're gradual and careful, then you can get the force in.
Consider another dramatic demonstration. Oh, this one is a beaut. Here is a vessel of water, and it has quite some inertia, and I put it on this paper, and I move it slowly, slowly. Remember, this has large inertia. It wants to remain at rest, and I am not trying to accelerate it too rapidly, and thereby friction.
So again, I'm just saying it obviously is moving, so it wants to remain at rest thing. It's not really putting up any resistance. It's just saying you have to put the energy in gracefully, and if you attempt to put it in too aggressively, I can't spread across all these atoms in the time you've given me, and so it ain't going to happen. You're asking me to make the conversion way too quick. I can't do it. So therefore, fuck you. Do as you wish. I can't help you. But it's not any built-in always consistent thing. It's something very specific to how you apply the force. So if you apply the force in a particular way, there's no resistance. You apply the force in some other way, there's complete resistance. So it's not really about it resisting. It's about compatibility.
Forces hold it onto the paper. And so I pull more and more and more and more. We're in a little trouble because friction isn't right for me. But anyone in his right mind must testify to the prospect, if I continue in the manner I have been doing, the whole thing will fall down. But if I invoke the laws of Newton, the first law, which says it wants to remain at rest and will refuse to be moved by short-lived impulsive forces, what?
All right, so there was no, in Newton's law, short-lived impulsive forces. That wasn't in Newton's law. It was like any force can change it, but there was no talk of short-lived impulsive forces. So, but obviously that is the catch. I mean, it probably should be part of the law, is saying it's really just about how you apply the force will decide if it's going to be able to accept it or whether it rejects it.
Watch it. Are you not surprised that it stayed there? Consider another, more application. Here is a vehicle, and here is a body standing upright in the vehicle. And now I want to show you that if I move the vehicle, the body is at rest with respect to it, and what does it want to do? It wants to stay there. Watch it. And so it did. And that's why when you accelerate...
Right, and so if he went slowly, it would be fine. So again, just pointing out that it's how you apply the force. So you have to match the acceleration to what the object is capable of moving. And if you're accelerating it faster than it's capable of moving, because it has too many atoms to accelerate to that speed, then some of them are going to be left behind, so to speak. And that's what really happens with a stick, right? It's kind of obvious. Some of them are going with the truck, some of them aren't.
Car rapidly from a standstill, your head is jerked back because of the large inertia of the head. On the
Yes, mass of the head. Yeah, so again, and how far it is from the point of contact. So the head ends up being far away from the point of contact. It's lagging way behind. It hasn't absorbed the energy. It's out of luck.
On the other hand, if the car is moving uniformly, if I now suddenly arrest its motion, what will the block do? Well, the block was going straight, and that's what it wants to do. Oh, notice I accelerated too fast the first way. There it is, and the block tipped forward. A quick one for your inquiry. Here I have two vessels, and remember the subject is inertia. They each contain 1 pint. And let us say that one is filled with cream and the other with milk. So I have a pint of milk and a pint of cream.
Yeah, you do have to think about this one. I mean, we did come up before. The cream is fat, so it's got a lot less density than water because it's got a lot of crap in it.
Quickly, which has the greater inertia? That's equivalent to asking which has the greater mass. That's equivalent to asking which has the greater weight. And
there we go. So at least we're getting somewhere. But a weight is a velocity. You have to have the component of velocity to have weight. Gravity's giving you a velocity. That's why you have weight.
Led to say, oh, the cream, of course, because it's thick and sluggish and viscous. Oh, no, mistake. The milk has the greater inertia for reasons, of course, you see clearly yourself. The pint of milk weighs more than the pint of cream. Another demonstration of the inertia again. Here is a stack of coins. They happen to be Australian pennies. Why? Because they have larger inertia than U.S. pennies. And now what can I do? With a thin blade, I can deliver a sharp, impulsive blow to the lowermost one. And what do I hope to see? I hope to see the whole stack remain unmoved. Why? Because it's at rest and wants to...
They're probably worth like $5 each now, right? Something like that. That's funny.
There it is. There it is. There it is. And I just love that demonstration. Why? Because it is a classic revealing the beauty and strength and simplicity.
So again, what it's displaying is that it's all about the velocity, and the fact is the object can't absorb the velocity you're imposing, and that's causing a consequence. Okay, so period. I mean, it's not about the fact that the other pennies don't want to move. It's just that you aren't supplying the energy in a form they can absorb. So again, if you pushed on the whole stack slowly, the stack moves fine. Push on it fast, it can't do it. Falls apart, so to speak. The bonds between the atoms break down. The bonds between the pennies, in this case.
In a sense, of Newton's first law. I want to show one more. Remember what the second part of the law said. I would urge you never to forget that the first law has two parts, which are rarely ever properly separated. I said a body moving in a straight line wishes to continue so. Here is a ball swinging in a vertical plane, in a vertical circle. I would remind you that at the instant in question when the ball is right there on the end of the string, its motion is tangent to the path at that place, and if I should cut the string or let go of it, the ball would not go radially outward, but would go instantaneously in a direction tangent. So, this introduces here, in a passing way, the idea of centrifugal force.
Yeah, it just introduces the idea that you're applying two forces. You're applying the turning force and the velocity of the ball by rotating, processing. Okay, so that's it. There's two velocities.
Which is a nasty thing to handle, and often much is said that is wrong. But if I let go of the string at the top, where will the ball go? Tangent. Watch it. There it is, tangent. Now, it is proper, before we conclude a program on Isaac Newton, to show you one of many photographs of Newton.
Yeah, it's not a photograph. But anyway, it's a painting. Photograph of a painting.
A very important place this man occupies in the history of humankind. And I would hope that when you go to London sometime, you will most certainly go to Westminster Abbey and see where he is buried. And what does it say on that beautiful...
Dead guy. Whatever. It's just so... Go visit the dead guy.
epitaph, among other things. Let men rejoice that so great a one has existed. So we are coming shortly.
So again, all of that, well, frankly, everything that will happen eventually. So you could argue that it doesn't matter who invents the first round wheel, right? I mean, it's coming eventually. So, I suppose there are people that make unique contributions. There may be contributions that save us 100 years. So you could argue that Newton, saved mankind decades in terms of getting us to the future faster.
To the end of the program. One final.
But the sad truth is we didn't do anything with that future. Didn't build on Newton's insights. We perverted them and distorted them, and fuck the game.
Enchanting thing. An array of cups. If I put this heavy block on them gently, I can drive this spike into that block without the cups feeling anything. Why? Why? Because the block has enormous inertia. If, on the other hand, I drop it, it's going and it wants to keep going. There it is. And thus I conclude, ladies.
Yeah, one thing took a lot more energy than the other. But anyway, obviously it was a lot more momentum, being applied to the cups by dropping the giant mass. But anyway, all right, so that's it. So might as well go with the ending tune.
A program on inertia, and I thank you for your attention.
All right, so maybe we'll do the next one the next time, and maybe I'll just call this a video. Sort of made my points. 300, more than 300 years they've had this theory. They haven't produced any really simple experimental evidence of the existence of the extra joules of energy claimed to exist in these lighter things going faster. So they never demonstrated that the bullet does more actual work in the universe than the energy of the recoiling gun. That if you found some way to collect the heat, convert all of their motion into heat, that they have this huge differential, that the bullet will create so many more watts of heat than the gun. They haven't done that experiment. They haven't done any of these experiments to demonstrate the existence of this four times the fuel to go twice as fast. I mean, these are bold assertions. 8-pound bowling balls going 16 miles an hour knock down twice as many pins as 16-pound balls going 8 miles an hour. No evidence of it, and all the evidence is counter, in the sense that no professional bowler can find any increase in potential by going to a lighter ball. None. All right. Yeah, it's just, and yet these aggressive, slanderous, argument that somehow I'm so egregiously wrong, and yet they can't produce any real evidence demonstrating I'm wrong. All right. So till the next time, and such and so forth and whatnot. I think that's enough. I feel like it's enough. I'm tired enough, so we'll call it enough. I have to go to work anyway, do some work.